Now we solve this problem of problem 59. Says that a particle slides on the surface of a fixed smooth sphere, right? So from the topmost point, that means there is a particle here and it starts sliding in this direction. Sliding in this direction. Find the angle rotated by the radius through the particle. That means there is a radius through the particle, which when it lifts contact with the sphere, let us say this angle is theta. This angle is theta when the particle is here and the particle has a tangential velocity v, say, and it lifts the sphere. You must have observed that it is the same kind of a problem of pendulum problem. But pendulum was actually swinging from bottom upwards. Here, the point is swinging from top downwards. And try to recollect, we have only two sets of equations. One set of equation is equivalence of energy. That means starting energy, starting kinetic energy, potential energy, whatever it is, the total energy at the start and will be the equal to the total energy at the end. And we have a force equation. If the point is here, it has a downward force mg and it has a radial force mg cos theta. And this mg cos theta provides the centripetal force, which is equal to mv square by r, where r is the radius of the sun, right? Now let us consider this is r. Let us consider this is r. Radius of the circle is r. Then, interestingly, the method is same. Let us say this point, let us name this point P, and let us name this point A, and let's name this point O. At P, you can write this here, at P, mg cos theta, the force equation, provides the centripetal force mv square by r. Same thing happened in our pendulum sums also. From here, what do we get? V square is equal to Rg, m gets cancelled, is equal to Rg cos theta. This is second thing, as I said, we have to think of the energy equivalence. It started from here. At this point, it's just started. It did not have any kinetic energy. It had only potential energy. So we write potential energy U at A will be equal to potential energy U at T plus the kinetic energy E at T. There is nothing else to remember, right? From here, we get potential energy at A. This is the datum point, mind it. This is the x-axis. We are making all measurements referring to the this horizontal line. Potential energy A at A was mg into r, radius r. mg radius r equal to potential energy at T is mg And what is this height? This height is r cos theta. R cos theta. So this is mg r cos theta. Plus, what is the kinetic energy at P? Is half m v square. V square we already got here. We bring it from here. Is r g theta. That is all we have. Nothing more we have with us. Here, mgr, 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 everything gets cancelled. So what we have is 1 is equal to cos theta plus half 1 equal to cos theta plus half cos theta. Therefore, by 2 cos theta is equal to 1. Therefore, cos theta is equal to 2 by 3. Therefore, theta is equal to cos inverse 2 by 3. That is the answer. I repeat once again, please remember for pendulum or all these problems in this chapter, you have only two things to handle it. One is energy equivalence equation, another is force equivalence equations. Utilize these two approaches little intelligently, you will definitely find the answer. Next question, we shall take the next question also in this session. Next question is, here it says, a particle of mass m is kept on a fixed smooth sphere of radius r at a position where the radius through the particle makes an angle of 30 degrees. That means to start with, it is kept at an angle 30 degrees. Let us say makes an angle 30 degrees with the vertical. This is to be noted. So let us say this is 30 degrees with the vertical. So initially the particle is here. Start with the particle is here and this angle is θ. And its radius has been told that radius is r. And mass of the body m also has been told. Right? And then it is released. What will happen? Particle will slip and at some point it will lose contact with the surface of the sphere and it will fall down to the ground. Right? And when it will lose contact with the surface of the sphere, that is when mg cos theta is no more equal to the centripetal force. Then it will lose contact with the ground. The same method, same problem. The first question that they have asked is, what is the force exerted by the sphere on the particle just after it's released? So immediately after it is released, the force exerted is nothing but mg cos 30, is nothing but mg cos 30, nothing but mg cos 30. So part A of the problem, reaction force is equal to mg cos 30. Cos 30, you know, is root 3 by 2. So it is reaction force is root. So first part is phi. Second part says, find the distance traveled by the particle before it leaves contact with the sphere. Now this particle will start moving, and at a position, let us say this is the position. I do not know what will be the correct position that we have to find out. Let us say this is the position, and let us say this angle is, let us say this angle is phi. Let's say this angle is phi. At this angle, and what they wanted us to find the distance. That was the distance traveled by this. Now, we should not worry about the calculation of distance, because we always know that the arc divided by radius equal to the angle in radian. So if we can find out phi, then phi minus 30 degree will be the angle, and from that angle we can always find out the arc covered by this particle. So once again, at B, say at this point its velocity is v. At this point its velocity is v. So force equation is m v square by r is the centripetal force, will be equal to mg cos phi, because now the angle is phi, mg cos phi. From here we get this square, m gets cancelled, is rg cos phi is equal to rg. From here you get v square equal to rg cos phi. This is the force equation. As I said, the second option that you have is energy equivalence equation. So instead of now, since these problems are similar, so instead of writing the whole thing once again, what do we do? What is the potential energy at, say, we have not given name of this. Potential energy here at this point is mgr cos 30 degree. mgr cos 30 degree, which is cos theta, right? Here it is mgr cos mgr cos 30. mgr cos, let us, it will be easier for me if we write theta, because writing 30 is sometimes problem. mgr cos theta. This is the potential energy at the beginning. Potential energy at the beginning will be equal to potential energy at the end. That means mgr phi plus kinetic energy at the end. That is half m, and what is the v square is rg cos phi. rg v square is rg cos phi. Now in this equation, all mgr gets cancelled. All mgr gets cancelled. So what we have here is cos theta. Here we have only cos theta is equal to cos phi plus half cos theta, right? Now, so energy equation, this mgr cos theta is the potential energy at, let's give it a name A, and this is B. Potential energy at A is equal to mgr cos phi is potential energy at B plus half mv square is the kinetic energy at P. Right? From here we get, so cos phi. So we have mgr cos theta is equal to mgr cos phi plus half mgr cos phi. So this is not cos theta, there was a mistake. This is cos phi, half mgr cos phi. So what we have, this is equal to 3 by 2 cos phi. It's equal to 3 by 2 cos phi. Therefore, we have cos phi is equal to 2 by 3 cos theta. Now we write the value of cos theta. Otherwise, now cos theta is cos 30. Cos 30 is root 3 by 2 is equal to 1 upon root over 3. From this, if cos phi is 1 upon root over 3, you can find from your calculator phi is equal to 54.73 degree. Now theta was 30 degree. So phi minus theta is equal to 4.73 minus 30 is equal to 24.73 degree. This 24.73 degree, if you calculate, is 24.73 multiplied by pi by 180 radian. This is equal to 0.43 radian. 0.43 radian. And so what is the distance traveled? We know arc by radius equal to angle radian. So arc or the distance traveled is equal to 0.43, 0.43 R. So this is the answer, 0.43 R. So this distance traveled from here to here is equal to 0.43 R. That is the answer. And we shall go to the next question and try to solve this.